Hello and welcome to my talk, System Transparency and its bootloader implementation as stboot. My name is Jens Drenhaus and I'm firmware developer at 9element Cybersecurity. We started the project back in 2018 as a secure and robust network bootloader. It then turned into an own open source project, and it's a collaborative effort by Mulvat VPN and 9element Cybersecurity. The project was introduced at last year's OSFC by Frederick Stromberg and Kai Michaelis. To get an idea on what system transparency is about and learn about its concept, I can highly recommend reading Rasmus Dahlberg's blog post, Hold On to Your Head and Learn System Transparency in 5 minutes. Since this talk will focus on the project's bootloader implementation, feel free to take a look at our other talks as well as Mulvat's white paper to learn about the big picture. To sum it up, system transparency empowers operators and users to verify and trust services running on a remote host. Therefore, techniques such as measured and remotely attested boot and reproducible builds are used. And of course, the system is based on open source firmware. The approach is to have the operating system separated from the host. There isn't any root file system on it. Instead, the operating system, together with the user space software, is bundled, self-contained, and reproducible so-called OS packages. These are publicly available to users who can audit the code and thereby know how their data is processed on a machine running this OS package. On the other hand, there is the host, which runs an OS package by performing a measured boot. So the host makes use of a TPM chip and extends the TPM platform configuration registers with hashes of each boot stage, including the OS package. Once booted up, the expected state will be remotely attested. Finally, to give trust to the users regarding the OS package running on the host, we plan to bring up a transparency log and insert reproducibly built OS packages into it. Okay, so let's take a look at stboot now. Since it is the project's bootloader implementation, it obviously runs on the host, and it currently supports to load OS packages either from a web server, a so-called provisioning server, or from local storage, in case you do not want to have network connections. All right, so for the course of this talk, I would like to give you some insights of the architecture of stboot, how it is implemented, what are the concepts, which features are included. Further, I will tell you about the different installation approaches with respect to different server fleet scenarios. Finally, let me guide you to our tooling repository, enabling you to start playing around with stboot and give it a try for yourself. This will include a quick demo as well. Let's start right away. stboot is a Linux boot distribution. This means it uses a Linux kernel together with an init.rmfs as part of the firmware. The code is executed in the init process of this init.rmfs. To set up an init.rmfs including the stboot code, we are using uroot. Actually, stboot is part of the uroot project and thus is written in Go. You can find the code at the uroot repository. For the most recent state, switch to the stboot branch there. At the moment, stboot is under active development and we plan to have it production ready at the beginning of next year. The code is mainly divided into 3 parts. First, there is the actual code of the init.rmfs init process I've talked about. You can find this code in the commands directory. This part is responsible for the main boot flow, including system tests, loading OS packages, doing measurements, and finally kexecing into the operating system. To do so, this code makes extensive use of the stboot core library, which you can find in the packages directory. The library provides functions and data structures for handling OS packages and its signature verification process. The core library is also used by a utility program called stmanager. This tool can be utilized to create and sign OS packages. I will cover the details in the further course of this talk. So now that we got the code, what else do we need in order to get stboot working? First of all, we need an OS package to be loaded by stboot. So you can take an OS kernel and corresponding initramfs and call stmanager create to get one. Actually, what an OS package is, it's just a zip archive including the boot files and some metadata. The important part in this step is that the OS initramfs contains the complete operating system, including user space software. At the moment, we are using a patch version of Debos together with the Bootstrap to create such an initramfs for Debian and Ubuntu. For Debian, it is already reproducible. It is possible to add a tboot kernel and an appropriate authenticated code module to the OS package in order to make use of Intel TXT. Once you have the OS package, you need to sign it, and therefore you need a self-signed root certificate. From this root certificate, you derive certificates for each one who should be allowed to sign your OS package, meaning each of those certificates must be signed by your root certificate. A call to stmanager sign will then take the newly created OS package, the signing certificate, and the corresponding private key as input to add a signature for this OS package. Note that the certificate will be stored together with the signature for the OS package and will be loaded together with it. The root certificate instead is packed together with the stboot code inside the Linux boot initramfs. This process can be repeated multiple times, so you can have more than one signature for each operating system package. I will come back to this later when talking about the signature verification as part of the boot process. A side note regarding the signatures and how they are added to the OS package. We ran through a couple of approaches here. Started from just appending a single signature at the end of the zip archive to including multiple signatures inside the zip archive. Our current solution is to have the signatures in a separate file now. So there is a, for example, mypackage.zip containing the boot files and a corresponding mypackage.zip.zix file containing its signatures and corresponding certificates. Okay, so we have the code and we have a signed OS package. What else do we need? We need two special partitions to be present on the host. One with the GPT label stboot and another with the GPT label stdata. The latter one, stdata, is used to store OS packages files in the case where stboot is configured to load OS packages locally. But even when stboot is configured to load OS packages via the network, there is the option to enable caching OS packages for the next reboot. These cached OS packages are also stored at the stdata partition. The other one, stboot, is used to store boot files depending on the installation option. I will cover that more precisely in the section about installation options. For now, keep in mind that stboot is a Linux distribution and consists of a kernel and an initramfs. So by boot files, the Linux boot initramfs is meant, for example. The other important file on this partition is a JSON file called host configuration. It defines network configuration, for example, if DHCP or static IP should be used, the URL of the provisioning server so that stboot knows where to load the OS package from in case of network boot, as well as the host identity and authentication. Speaking of configurations, let me dive deeper into this. So beside the host configuration on the stboot partition, there are further data and configuration files which packed into the Linux boot initramfs together with the stboot code. These are the HTTPS root certificates to establish connection to the provisioning servers, the signing root certificate I spoke about during the explanation of creating OS packages, and a further JSON file in addition to the one on the stboot partition called security configuration. This one defines boot mode, either network or local, the minimum number of signatures that must be valid. Remember that you can sign an OS package with more than one signature. And last, a flag that determines whether the OS package should be cached when using network mode. The configuration is separated for several reasons. Firstly, all values in the host configuration file on stboot are likely to be dependent on the individual host, like identity, IP address, and so forth. Secondly, the configuration inside the init.rumfs is more critical in terms of security, and since they are part of the Linux boot init.rumfs, they will be measured to the TPM and thus affects the remote attestation. Okay, that's it for the different components. Let's see how all this works together now by taking a look at the boot flow. The first steps are quite straightforward. Mounting stboot and stdata partition and checking for all required configuration and data files and validate them. Next up, a txt self-test is performed to evaluate if the host is capable of Intel TXT. Now the OS package is loaded either from the stdata partition or from the network by establishing a connection to the provisioning server. Loading the OS package involves both the zip archive itself as well as the corresponding zip.zix file we know from the creation of OS packages. Signature verification. This is one of the most important parts. As mentioned, the certificates are stored together with the signature in the zip.zix file. The root certificate, on the other hand, is part of the stboot installation. So first, the certificate is validated against the root certificate. Then, stboot checks that there is no duplicate certificate inside the zip.zix file. And then finally, stboot calculates the hash of the actual OS package file and verifies the signature with the help of the validated certificate. This process is then repeated for all signature certificate tuples in the zip.zix file. The last step is that the number of valid signatures must match the number configured in the security configuration file. In case one of these steps fails, stboot will not boot the system. Anyway, if everything is fine, stboot will go on and extract the boot files from the OS package. Depending on the content, stboot will extract the OS kernel and the OS init.rumfs only. However, if stboot finds a tboot kernel inside the OS package and the host is capable of Intel TXT, stboot will set up the OS kernel and the OS init.rumfs as multi-boot modules of tboot. Afterwards, stboot expands the PCRs of the TPM with the hash of the OS package, and finally uses kexec to hand over control to the operating system or tboot respectively. This was it regarding stboot's architecture. Next, let's move on and have a look at the different ways how you can install stboot on your system. Regarding this section, keep in mind that stboot is a Linux boot distribution, which means there is a kernel and an init.rumfs. Okay, so obviously the most robust and straightforward option is to have stboot as a payload of core boot. In this case, the stboot partition only contains the host configuration and no further boot files. Due to the fact, however, that you might not have a server fleet where you can flash core boot to all of your machines, we came up with an approach for this scenario which we call MBR bootloader installation. In this installation option, works on machines with EFI firmware as well as legacy BIOS firmware. The Linux boot kernel and initramfs are stored on the stboot partition. A basic bootloader written to the master boot record of the stboot partition will then bootstrap the actual stboot bootloader. With this installation option, there is a lag in the measured boot chain, since syslinux, which we are using as the basic bootloader in the MBR, does not support TPM measurements. It's definitely future work to change syslinux to some very basic bootloader which supports measurements. So in case you have any ideas, feel free to share them. Last but not least, there is a third installation option for UEFI systems. In this installation option, the Linux boot kernel and initramfs are bundled and compiled with the EFI stub kernel option enabled, and once again stored on the stboot partition. Additionally, the stboot partition is marked as an EFI special partition. Thus, stboot is loaded and executed as an EFI application. The idea is to use the TPM measurements of the EFI firmware. We tried it successfully with secure boot being disabled. But we somehow have to make sure that the measurements will be done always, even if secure boot is disabled, since we want to have measured boot, not trusted boot. All right, so that's it. These are the 3 installation options for stboot. I hope you are thrilled to get your hands on stboot now, so I will show you where to go. In order to get started with stboot and try it out, just visit our tooling repository. It will serve you as a framework to build and arrange all the components you have heard during this talk. We will continuously update the descriptions in the README while development goes on. The different steps are explained there once again, so check it out in case my little tool confused you at some point. The easiest way to get started is to call the run script, which will guide you through the different steps. It's recommended to run this whole architecture and run these all scripts on a Ubuntu system. But now, let me give you a quick demo. So, when you're in the system transparency repository and will run the toolchain for the first time, configuration file will be generated, which looks like this. And in here you have all the different variables which controls the behavior of stboot and ends up in the different configuration files. For example, here you can see that we are currently configured stboot in local boot mode. Okay, so as said, let's just call the run.sh script. And we do not want to overwrite our configuration. And since I've already installed the toolchain, we will skip this step. And also I have created all my keys and certificates, so we do not run this either. Building the operation system would be the next step, but this actually takes quite a bit of time. So I've prepared that and we will skip that for now. Here you can choose between different operating systems we have in our in the repository at the moment. All right, now there is a wrapper script for stmanager, and I want to show you this. So let's run it. And it actually calls stmanager create to pack the boot files from the former created operating system into an OS package. So give it a couple of seconds. There we go. We have created our new OS package with a timestamp, and you can see it's a zip file. Now, the script does several calls to stmanager sign to hash the contents of the OS package and add signatures to it using some example signing keys you can see here. this will be repeated 5 times, so it will take another couple of seconds, but you can see that the SD Manager will print to you how many signatures are included in into the OS package, so you can so you know if you want to hand it over to another operator or if you want to sign it. Once again, depends on your configuration and depends on your needs. Right, third one is gone. Come on, fourth and fifth. Of course, it takes ages now in the presentation. Usually it's done a bit faster, but I guess I have a bit of time left, so that's fine. Okay, there we go. Last one is the process. All right, it then automatically creates a file which names our created OS package, and it gives you some information of how you can use SD Manager. Next step would be to upload our package to a provisioning server, but since we configured stboot for local boot mode in this scenario, we will skip this one, and then come to the core part and actually build our installation option. And I will choose the MBR installation option in this time. So by running this, oh, sorry, need to choose a number here. So by running this, it will create our two partitions, so stboot and stdata partitions. It will print you all the configurations, which it takes from the configuration file so that you can see that everything is nice and set up correctly. And then it builds the Linux boot kernel. Actually, the Linux boot kernel is built. It will just include the init.fs in it. And then finally, it constructs a disk image from the two partitions, which you can use, for example, to DD to your legacy system. Here you can see that the boot partition is marked as a bootable partition. And here, the stdata partition contains the OS packages for the configured local boot option. And now finally, we can give it a try and test it in QA mode. So since we built MBR bootloader installation, let's choose 3 here as well. And we can see it going. All right, now the Linux kernel is booting up. Then there is uroot, stboot. All the configuration options are printed out. So the security configuration option and the host configuration option. And now it has mounted the stdata partition. You can see that because we're in QA mode, TXT is not supported. And it has loaded our OS package from the data partition. And now it's opening it up. And then all the contents of the OS package is printed out. There you can see why it took so long. There are many authenticated code modules included in here. And then signature verification is passed. So everything is fine. Found 5 signatures. 5 are valid, but only 3 are required. So everything is fine. And then it gets measured into the TPM. And then the control is handed over to the operating system. So you can see the kernel here. It's a Ubuntu system inside this package. And the next step would be kexec. So there it is. Kexec, starting new kernel. There we go. Ubuntu kernel booting up. Of course, because the initramfs contains the complete operating system, including user space programs, it takes a bit to unpack it. I'm doing the presentation on my small laptop, so maybe it's not as much power as a server. But there we go. Welcome to Ubuntu. There we are. All right. The rest is just, I guess, systemd coming up here. But I guess you got the point. So let's see. There is a login. All right, there we go. Yes, so that's it, actually. That was the demo. Thanks for listening, and I appreciate your feedback. So let's meet in the Q&A session. Thank you.